Our primary objective today is to thoroughly discuss the Litterman approach. So I'd like to begin by explaining the fundamental mathematical concepts that lie behind it. The fundamental concept behind the Litterman model is to effectively combine or shrink two distinct methodologies for determining the expected return of assets. This is achieved through the sophisticated technique of Bayesian precision weighting. Essentially, what this means is that we are dealing with two different, often competing approaches to forecasting future returns.
That we would like to be able to accurately determine the weighted average between these two different approaches.
It's important to remember as a crucial point that when we are working on solving for the optimal portfolio, the fundamental and most significant rule we must apply is to take the inverted variance-covariance matrix and then multiply it by the expected return associated with each individual asset. So we're now going to be considering and specifically targeting this important column matrix. This particular column matrix, as you can see, actually contains the expected returns for each of our individual assets, be it asset number 1, asset number 2, asset number 3, and so on and so forth. The Litterman will strive to minimize the error in its estimation process by employing a specific weighting mechanism, one that is related to Bayesian principles across two distinct models. So our initial model is fundamentally based on the equilibrium concept, and then the second model, distinct from the first, is built upon what we call the view model. Now, this view model, as an illustration, possesses an inherent subjectivity, meaning its parameters can often be directly influenced and ultimately determined by the individual analysts involved. However, in this particular case, within the context of our specific approach, we have chosen to consistently utilize the historical mean. So, by calculating the historical average for each asset, we're going to then determine. So we have these specific numbers right here. And this particular set of data would then serve as our primary candidate for what we consider the expected return, essentially our initial viewpoint. Our second approach involves considering the equilibrium return, which is precisely what a specific financial model would determine. As an illustrative example, we could readily employ a methodology quite similar to what is known as the standard market model. In this particular scenario, we're going to proceed by assuming the presence of this variance-covariance matrix. And as is standard practice, we recognize that it's organized into distinct columns and rows. This first part reflects the variance of the first asset. This next part reflects the covariance of the first and second asset, and so on. That's precisely why we refer to it as the variance-covariance matrix. Now, when considering the market model, we have the option to use either equal weights or the market value weight. Given that we do not possess the market value data, it will be simpler to proceed with the equal weight approach. Specifically, in this particular scenario, as we are dealing with three distinct assets, the equal weight calculation is simply 1 divided by 3, which results in 0.333. The very first thing that we are required to do in this particular process is to multiply the assigned weight by the variance-covariance matrix. And the fundamental idea here is that we absolutely need to accurately measure the risk sources for each individual firm. Based on the level of risk, we are going to determine the appropriate compensation. So, for example, considering the first asset, we identify a primary risk associated with it, which is its inherent variance. Additionally, a secondary risk arises from the covariance of this asset with the second asset in question. And the third source, which is derived from the covariance of this specific asset with the third asset. So these are essentially the three distinct sources that we are considering. If you then proceed to multiply each of these by the corresponding weight for each asset, subsequently, we will proceed to construct a vertical array, commonly known as a column matrix, which will contain specific numerical entries. Then, to properly adjust for potential downsides, we multiply by the appropriate risk compensation. This crucial risk compensation, as you might expect, is directly influenced by the prevailing level of risk aversion. Consequently, a significantly higher degree of risk aversion will always demand a much greater amount of financial compensation for assuming any kind of risk. Once we take these numerical values and multiply them by the appropriate risk aversion coefficient, we then arrive at the expected return that the investor demands for each individual asset. This particular situation demonstrates how we effectively utilize this equilibrium model. Therefore, we're setting the requirement at 4% for the initial asset, then 8.8% and 14.5% for the third asset, all based on our established market model. Consequently, we have two primary candidates to consider here, specifically the equilibrium model and the view 1. And for our calculations, we consistently utilize the historical mean, just as we previously discussed. So this initial calculation will provide us with the expected return for each individual asset, and this particular approach will yield precisely the same outcome. So the key question then becomes, what is the final column matrix of returns that we ultimately need to consider? Ultimately, it will represent a carefully weighted average derived from these two distinct candidates. So, in order to effectively apply the Black-Litterman framework, we are required to accurately determine both the precision and the inherent uncertainty. And this fundamental requirement is precisely why we absolutely need to define these specific parameters. The very first parameter we must consider is known as tau, and its primary function is to accurately reflect the degree of uncertainty present within the equilibrium model itself, this particular value. This particular variable, k, specifically the lowercase k that we see here, serves to represent the inherent uncertainty that is present within the view return matrix. And of course, we absolutely need the risk-free rate because we're dealing with the Sharpe ratio. When we are dealing with the calculation of a Sharpe ratio, it becomes imperative that at the very end of our process, we deduct the risk-free rate from the overall expected return. Consequently, these are the crucial parameters that we will need to precisely define and establish. Moving forward, as we proceed, we must then determine the inherent uncertainty present within each individual model. Lasha, when we're dealing with the equilibrium calculation, we proceed by multiplying a specific constant number, and this particular constant, for the sake of our current example, is specifically defined to be equal to the value of 0.05. So you'll need to multiply that specific constant number by every single element within the variance-covariance matrix. This process will then yield a completely new matrix, and from that resulting matrix, we then extract the diagonal term. So we've established the uncertainty in this area. However, it's also crucial for us to determine the uncertainty specifically related to the view matrix. Given that we perform an independent estimation for each individual asset, we must therefore depend solely on the diagonal term of this particular component. And once we've done that, we then multiply it by the k factor. Remember, the k is directly related to the view return matrix, and its value was previously stated to be 0.1. So once we've completed that, we will then obtain the omega. So, this reflects the inherent uncertainty associated with these metrics, and that also reflects the uncertainty for the view metrics. Next, we need to determine the precision. Precision is quite simply the inverse of that. So if we have high uncertainty and then we take the inverse of that, we are going to end up with a low value, precisely because there's an inverse relationship between uncertainty and the concept of precision. Therefore, by simply taking the inverse, we are effectively finding the precision. When we take the inverse of the omega, which is directly related to our specific view matrix, we will then be able to obtain this crucial variance-covariance matrix. Okay, so the inverse of our variance-covariance matrix, which we've been working with, is actually this specific matrix right here. Following that, we then proceed to multiply this result by the inverse value of our chosen parameter. To be precise, the inverse of a 5% value, or 0.05, is exactly 20. As we've previously established, we have already successfully determined the inverse of that variance-covariance matrix. Therefore, the final inverse of this entire expression will ultimately result in this particular matrix. So first we consider the inverse of omega, then we also take into account the inverse of the uncertainty that's directly related to our view matrix. This particular combination, this entity, is precisely what we define as a precision matrix for each individual model we're working with. And once we have that established, our next step is quite straightforward. We simply need to solve the primary equation. The equation states that to accurately determine the expected return, specifically following the Black-Litterman framework, we first need to take the precision associated with each individual model, then multiply that by its respective return metrics, and finally, we must divide this entire product by the aggregate or total precision across all models. Therefore, in this specific instance, our objective is to determine the value of term A. This particular term A fundamentally signifies the entire precision. So what we're observing here is the precision value specifically calculated for the K-view model. And then moving along, we have the precision that is directly related to, more precisely, this particular data point clearly shows the precision connected to the view model itself. And this next one illustrates the precision that's associated with the equilibrium state. Ultimately, this final figure represents the actual equilibrium number, the market model. Once we've added the total precision value, we've just identified the appropriate denominator. Therefore, the final answer will be A. Our next step involves calculating the value of B. Here, B functions as the numerator in our calculation. We obtain this value by multiplying the precision metric by its corresponding related model. Consequently, this particular value represents the precision associated with the equilibrium return. Subsequently, we then multiply that result by the actual equilibrium return. Furthermore, we possess a crucial variable that is directly linked to the precision of the view model's output. Our intention is to then multiply this particular variable by the actual return value of the view model. This calculation is essentially performed as a weighted average, where the precision serves as the weighting factor. This particular step will then provide us with the necessary numerator value. Subsequently, we simply take the value of B and divide it by A. This operation would then yield the final expected return, which is derived specifically from the Black-Litterman model. It's important to note that the projected return or the expected return falls somewhere in the range between what our belief model suggests and what the equilibrium model indicates. To give you a concrete example, if we consider the very first asset in our analysis, its expected return, as determined by our specific view model, which is also known as the belief model, was precisely 8%, and just as a quick reminder, this particular 8% figure was derived directly from our reliance on the historical mean data.
When we consider the equilibrium model, the value we obtained was 4% and then 4.16%. However, in this particular case, the actual number falls somewhere in between those two values.
It could be closer to one of them specifically because we are using a weighted average approach. However, any number that we observe here will always be found between the two distinct models.
Considering the performance of the second asset in our portfolio, for instance, when we look at the data from the view metrics, we observe a value of exactly 10%. However, if we compare that to the results generated by the equilibrium model, the figure stood at 8.8%. Now, with our current analysis, it registers at 9.8%, which is naturally a bit more aligned with the initial view model's prediction.
Now, when we look at the third asset specifically for the view model, that figure came in at 6%. However, for the equilibrium model, the result was significantly higher, reaching 14.5%. So the actual value, which falls right in between those two, is 6.8%.
Okay, once we've got this particular value, then we're all set. We then proceed to simply calculate what's known as the excess return. Therefore, we'll subtract the risk-free rate from each individual data point. And in this particular instance, we've made the assumption that it stands at 2%.
And that process will provide us with the complete metrics for the excess return column.
And then to accurately solve for the maximum Sharpe ratio, since we already possess the excess return, you simply need to multiply that excess return by the inverted variance and covariance matrix to obtain the z value. And once we have obtained the z, simply we take the proportion of each z value by the sum of z, which we did that in the mean variance and other portfolio optimization approach. First, we invert the variance and covariance metrics, then we multiply that by the return, and we are done. This gives us the z value. From the z value, we then derive the proportion and consequently the weights. Once we've successfully determined the optimal weights, our task of defining the portfolio optimization objective is complete. Our mission here is accomplished. Now, with that understanding, let's put this into practice. We'll use our dedicated Finance Research Gate website for this. Specifically, I'll navigate directly to the time series analysis section.
Then, for our next step, I will proceed to select the monthly option from the available choices. We'll set the time frame, let's say, from the year 2000 all the way through to 2010. Once those parameters are entered, we'll then click the Apply button to confirm our selections. For this particular analysis, let's begin by focusing specifically on Series A.
For our analysis, we're going with a monthly return. This is the key variable that we absolutely need to work with. Now, to start, we can choose a few firms. Let's use 3 firms, just like in our previous example. So we'll select this firm, then this one, and finally this one.
And then we proceed to apply the filters.
Then we need to begin by activating the main portfolio section. After that, we'll proceed to enable the portfolio optimization function, specifically for our Series A investments. Following this, within the objective settings, we'll carefully scroll down through all the available options until we successfully find the Black Letterman model. Once we've located the Black Letterman, we will then select the maximum Sharpe ratio portfolio optimization strategy. Let's consider using a simple covariance estimator, specifically sample 1, and for this we'll utilize, for instance, 12 observations to accurately estimate the necessary parameters. So in this particular case, we are primarily dealing with variance parameters and also with covariances. Ultimately, we are dealing with a financial return. How many object observations are we planning to use for estimating these input parameters? We are currently using data from the past 12 months, but we can certainly increase that number. And we will be repeating this process month after month because each month will receive a new observation, allowing us to update the portfolio. So the solution here isn't just one single portfolio. It's a unique portfolio created every month until the end of the sample period. So we will maintain a long only position, meaning we won't engage in any short selling activities whatsoever. Therefore, the variable W, which represents the weight of each individual asset within our portfolio, must always remain strictly positive. Furthermore, we should avoid placing any strict constraints on the overall portfolio optimization process itself. And let's ensure we keep this particular value at a sufficiently high level. Then we can proceed to run the portfolio.
Now, once we are actively engaged with this task, it becomes absolutely necessary for us to modify the various parameters, especially if you find yourself not entirely satisfied with the initial configuration or the default settings that were provided. So, regarding your risk-free rate, it's important to note that it isn't actually zero. Let's just align the numbers with the example, which is 2%.
Okay, so the prior uncertainty we're discussing here is directly tied to the equilibrium uncertainty value, and that specific value was previously stated as 0.005. It's important to recall that this particular figure is exclusively for the equilibrium condition. Yes, it's indeed connected to the equilibrium as we've mentioned, so to reiterate, that's 0.005.
The risk aversion parameter is 2.5, and yes, it does indeed perfectly match.
And finally, we need to address the parameter concerning the level of care associated with the inherent uncertainty within our current view or belief model. This particular setting was previously established at a value of 0.1. Therefore, it is imperative that we now adjust and ensure this value is indeed brought down to precisely 0.1. Once that adjustment has been made, we will then proceed to execute the model simulation one additional time.
What we're looking at here is the out-of-sample performance. You'll observe that we achieved a Sharpe ratio of 0.68, which is quite respectable. We observe an annual return of 21% with the corresponding annual volatility at 26%. These performance metrics are certainly not bad. We can also take a closer look at the weight distribution. So for each month, we implement a specific weight solution based on the chosen portfolio objective. And looking further down, you can even compute a range of in-sample statistics, including measures like the mean, the standard deviation, and other relevant statistical indicators. For us as investors, our focus is primarily on the out-of-sample results because these represent the genuine future performance that will ultimately affect our financial outcomes. The in-sample results might appear superior when compared to the out-of-sample performance. However, for the out-of-sample situation, if we employ a methodology that relies on stable parameters, and this fundamental concept is what underpins the Black-Litterman model, the primary objective is simply to minimize the prediction error when we are estimating the expected rate of return for all the assets in question. So this approach could potentially yield superior out-of-sample performance when compared to an alternative model. And that concludes our discussion on the Black-Litterman approach. Thank you very much for taking the time to watch this presentation.